Hey guys, Mr. Palmer back with the second part of this equilibrium question involving N2O4 and NO2. And I just finished solving using the quadratic formula. I'd like to show you another way that you could solve this using successive approximations. So it's another way that we can solve this. So what I'm going to do is I'm going to take this expression that we had already created here, and I'm going to copy it over on the next slide. So we had the Kc equal to the concentration of the NO2 squared over the concentration of the N2O4. And our values we can substitute in. This was 2x squared on top, and on the bottom we had 0.12 minus x equal to 0.029. Now what we can do, instead of going through and using the quadratic equation, if we look at this expression, there's an easier way that we can kind of do this. This value here, because of our equilibrium constant, is not very large. This x in the bottom part of our equilibrium expression is going to be small. So the quantity 0.12 minus x is going to be approximately equal to 0.12. So what we can do is sort of set this x here on this part in the bottom and just say x is equal to 0. So it's going to be an estimate. It's not going to be 0. It's going to be some positive number, but it's going to be close to 0. So if we were to do that, that would give us 0.029 equals 4x squared over 0.12. And if we solve for x in this expression, it's going to give us 0.029. It's actually the same number as our equilibrium constant. Now, that's not the answer. We already know that we found it to be 0.026. Well, what do you do at this point? What we do, let me just switch colors, is that we're going to take this value, this 0.029, and we're going to substitute it back into our equilibrium expression for x. So what you can do at this point is we're now going to take that 0.029, we're going to substitute it back into our original equation. And if we do that, the 0.029 is our k, is equal to 4x squared over 0.12 minus what we calculated x to be, which is 0.029. If you do that, you then wind up with an x value, solving this expression, of 0.026. And what you'll see is that's the actual answer we found using the quadratic equation. If you were to substitute this 0.026 back into our expression again for the x, what you would find is that x would then be 0.026. What's going to happen is you're going to get the same value. And so once that happens using this method of successive approximations, you're going to wind up with the correct value the same way you did using the quadratic formula. So this is just another method you can use if you don't have a calculator, you can't remember the quadratic equation in order to set that up. So let's talk about these really important problems that involve qualitative understanding. This is a conceptual understanding of equilibrium. So we have three changes that we're making to equilibrium, and we're trying to figure out how these are going to affect the concentration of the NO2. So it's important that you understand we're looking at how do you affect the concentration of the product. So we want to be able to see whether it's going to shift to the left, to the right, is it not going to affect it at all. So the first one, we're increasing the temperature, and what we're going to look for is we're looking at the change in enthalpy. In this case it's positive, which means the forward reaction is endothermic. So we're adding heat to the left side. You can think of an endothermic reaction as having heat in the reactant side. So if the temperature is increased, that's going to cause the shift to the right, and that means that the N2O is going to increase. And you need to have both which way it's going to change as well as the y. So it's going to increase. Why is it going to increase? It's going to increase because of a shift to the right. And I'm just writing out the word shift right. I'm not writing a full explanation. And it's going to shift right because increasing temperature favors endothermic. Second part, part 2, additional N2O4 is injected at the reaction vessel. This if we're looking at Le Chalier's, here's our equation, our equilibrium expression. If we're increasing the N2O4 on the bottom, again, we're going to have to shift to the right, and that's going to cause an increase. Why is it going to increase? Because it's going to shift to the right, and you want to say that's because of Le Chalier's principle. Increasing the reactant is going to increase the product. Last part, part 3, is pressure. And so if we're looking at pressure in this equation, we need to look at the moles of gas. We have 1 mole of gas on the left, we have 2 moles gas on the right. Increasing the pressure of the container is going to cause a shift in the direction of left's moles, which means it's going to shift to the left. So we're going to have a decrease in the NO2 because we're going to have a shift to the left. And you want to say why it's going to shift to the left, and it's going to shift because increasing pressure favors less moles of gas. Right. And that's it for this one. I'll be back for part E and F in the third part.